So for y equals natural log of e to the x over e to the x minus 1, we want you to find the derivative of it. I think it says to find, what does it say, find dy dx, or does it just say find the derivative of it, or something like that? Where is that? I feel I have it. There we go. Yeah, find dy dx. So first thing I would do with that one is I would rewrite the natural log as y equals natural log of e to the x minus natural log of e to the x minus 1, just because that's something we can do with logarithms, right? And so from there, I would then take the derivative of this, and natural log of e to the x to begin with is just x. So in fact, I'd probably do this first, x minus natural log e to the x minus 1, and then I'd take the derivative of it from there. So dy dx should be 1 minus, and then the derivative of natural log of a function is 1 over that function times the derivative of that function. So we'd end up with 1 minus e to the x over e to the x minus 1. And if I look at the answer choices there, that doesn't look like it's one of the answer choices. So I would get a common denominator for this of e to the x minus 1. So that would become e to the x minus 1 minus e to the x over e to the x minus 1. And if I multiply 1 by e to the x minus 1 over e to the x minus 1, the e to the x minus the e to the x cancels out, and you're left with negative 1 over e to the x minus 1. And then looking at that, yeah, looks like that comes out to be choice C. Everybody good with that one now? Okay. So then what's the next one? 11. So 11, we've got y equals natural log of secant x plus tangent x. And for that one, I would just go straight into taking my derivative. Dy dx equals 1 over secant x plus tangent x. I gotta write plus in there. And then I'd multiply that by the derivative of secant x plus tangent x. The derivative of secant x is secant x tangent x. And then plus the derivative of tangent x, which is secant squared x. And looking at the answer choices, none of them look like that. So then I'd look at my numerator probably and see what can I factor out of my numerator. And I'd say that I can factor out a secant x from it. So that'd be secant x times tangent x plus secant x in the numerator over secant x plus tangent x in the denominator. And then tangent plus secant is the same as secant plus tangent, so those will cancel, and we'd just be left with secant x. And it looks like that's choice A. Everybody good with number 11 there? Cool. All right. So I'll do 12 right now because somebody else was asking for that, and then we'll get to the 21 through 24 because 12 is pretty similar to what we've just been doing. So for 12, we've got y equals e to the x minus e to the negative x over, what is it, e to the x plus e to the negative x. So this is just a quotient rule problem. So the derivative of this should be the denominator times the derivative of the numerator, and the derivative of negative e to the negative x should be positive e to the negative x. And the derivative of e to the negative x should be negative e to the negative x. And then that's all going to be over the denominator squared. Good or no? So far?
Good.
And looking at the answer choices, none of them look like that. So I distribute out my numerator. E to the x times e to the x is e to the 2x. E to the x times e to the negative x is e to the 0, which is 1, with another e to the negative x times e to the negative x would be another 1, so that'd be plus 2. And then plus e to the negative x times e to the negative x is e to the negative 2x. And then I'd subtract everything in the next one, which would be an e to the 2x. And then the e to the x minus the e to the negative x. And the negative e to the x times the e to the x becomes a minus 2. And then the e to the negative x, or sorry, the negative e to the negative x times the negative e to the negative x would become a positive e to the negative 2x. All over e to the x plus e to the negative x squared. Everybody good with that so far? Okay. And then from there, simplification should be pretty straightforward. The e to the 2x and the minus e to the 2x cancel. The e to the negative 2x and the minus e to the negative 2x cancel. 2 minus the negative 2 gives you 4. And e to the x plus e to the negative x squared, which looks like that one is, what is that choice? D. Any questions on that one? Everybody okay with that? How did I get the negative 2? This negative 2 right here? So that's e to the x times negative e to the negative x. So e to the x times e to the negative x is e to the 0, and it's a negative e to the 0. And then I have a second one of those for the other negative e to the x. Sorry, negative e to the negative x times e to the x. So I end up with 2 of those. Okay. Cool. All right. So those are those 3. Those are not too terrible, but a little bit complicated. And then the question was just about how to go about 21 through 24. So those ones are just implicit differentiation. You're looking for dy dx given that equation. So x cubed minus y cubed equals 1. So I can go ahead and do that one. 1 second. So let's do this x cubed minus y cubed equals 1 to start with. So that just becomes 3x squared minus 3y squared dy dx equals 0. And if we're solving for dy dx, we should get 3x squared equals 3y squared dy dx. And if we're dividing then by the 3y squared, we should be able to cancel the 3's. X squared over y squared equals dy dx. Does that make sense what you're supposed to do for 21 to 24 now? Okay, so probably good with the rest of those. And then I'm going to do 29 and 31 and then talk about 35 to 37. All right, so 29. 29 is x squared plus y squared equals 25. And we want to know at the point 0, 5, what is the value of the second derivative? So this is one where you have to be able to find a second derivative implicitly. So we did some of these way back when. First off, find the first derivative, 2x plus 2y dy dx equals 0. 2y dy dx equals negative 2x, and dy dx equals negative x over y if we cancel the 2's out. And then from there, to find the second derivative, we just take the derivative of this implicitly, so the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. And dy dx was negative x over y. So this should come out to be negative y minus, and then it's negative x times another negative x, which is an x squared over y. So minus x squared over y all over y squared. And we're supposed to evaluate that at the point 0, 5. So when x is 0, that's going to cancel out, right, when we evaluate it at 0 and 5. So we'll end up with negative 5 over 25, or negative 1/5, which was choice D. Makes sense to everybody? Any questions on that one? This x squared right here, is that what you're talking about? Okay, so dy dx is negative x over y. So negative x times negative x over y is x squared over y. Okay. What was the other one? I think somebody said 31. What's 31? 31, we're given f of x is 5 to the x, and that 5 to the 1.002 is approximately equal to 5.016. We want to know what thing is the closest to f prime of 1. Okay. So f prime of 1, then we could say is about equal to the slope between 1 and 1.002. So we could say that f prime of 1, we'll say this is the slope of f at x equals 1, is f prime of 1, which is approximately equal to, on a very, very small scale, the average rate of change on that interval, which would be 5 to the 1.002 minus 5 to the first over 1.002 minus 1. That's just an average rate of change type thing, which gives us 5.016 minus the 5 over the 0.002. And if we simplify that out, we've now got 0.016 divided by 0.002, which comes out to be, what does that simplify down to? Looks like that should be 8. Good or no? On that one? Okay, and then let me see, was it 35 to 37, right? Okay. So 35 is the limit as h approaches 0 of 1 plus h to the 6th minus 1 all over h. And so what we're looking at here is that this is just the limit definition of the derivative. And so we're looking at, and I'm going to write this out actually, the limit as h approaches 0, right? It's f of x plus h minus f of x all over h. And so we can see that the function that we're given is something plus h to the 6th, right? Well, that's our x. So this is x plus h to the 6th. So this must be x to the 6th. So we're looking at effectively the limit as h approaches 0 of x plus h to the 6th minus x to the 6th over h, which is the derivative of x to the 6th. And we want to evaluate that when x is 1. And so the derivative of x to the 6th is 6x to the 5th at 1, which is 6. So that's the first thing that we could, first way that we could go about doing those. But second, we could just look in here and go, well, if I plug in 0 for h, then I end up with 1 minus 1, which is 0, over 0, which is 0 over 0, which is indeterminate. And I could use L'Hopital's rule if I wanted to. And say, well, the derivative of 1 plus h to the 6th is 6 times 1 plus h to the 5th. The derivative of minus 1 is 0, that goes away, and the derivative of h is 1. And we would just plug in 0 for h and get 6 times 1 to the 5th, or 6. Does that make sense for that one? Cool. So do you want me to do one of the 36 or 37 that are the same, or are you good with those now? Okay. Yeah, probably better if you try and work them out on your own now that we've done one of them. Anybody else? Any other questions on those first 40 there? Okay. So over the next couple of days, we'll try and get through the rest of the ones in the derivatives. And like I said, I'll get up those ones that are missing sometime this afternoon. And in addition to that, I'm happy to go back and go over any of the other ones later this week from 1 through 40, or the limits if you were a little late getting started and still have questions on some of them. So I think that should be good on our review for now. And like I said, I'll get some applications of the derivative and integral ones up soon, today or tomorrow. So what we're going to do now is move in to volume. And volume stuff starts to get a little bit more complicated than the area stuff. We're going to start today with what we call the volumes of solids with known integral cross-sectional areas, which seems like a lot, but seems confusing. But it's not that bad. What we're talking about is things like, and they won't be this simple, but things like a cylinder. There's a cylinder, right? Everybody's familiar with a cylinder, I hope. If I were to take this cylinder and suppose this is lying flat on the ground like this, and slice it vertically, and take the two pieces that I get when I sliced it completely vertically and opened it up and looked at it, what would the cross sections be? What would the two shapes I'd be looking at be?
Circles.
Right, I should get cross sections that are circles, exactly. Cross sections are circles, perfect. And do we know the area of a circle formula? We should, right? It's pi r squared. So if I can find the area of one of those cross sections, I should be able to find the volume of the entire thing. And how do we do that? Just don't think about an integral for a second, but how do you find the volume of a cylinder? Well, you take the area of this base, right, pi r squared, or in other words, the area of a cross section of it, and multiply it by the height. True? Isn't that how you find the volume of a cylinder?
Yes.
Yeah. So from there, we should be able to sort of think about this in terms of integration and in terms of summing together an infinite number of little things here that we want to sum together. So I could take a slice of this and think about it as a slice that is as thin as you could possibly slice out of this cylinder, right through the middle of it, right? Now that those crossed each other, but taking as thin a slice as I can. Imagine this slice, except, you know, a million times thinner than that, and then a million times thinner than that, and a million times thinner than that. The thinnest possible slice you could get. It's almost like it doesn't have a thickness to it, right? True?
Right.
But it does, right? Because there's no way to make it have no thickness. And so if I sliced one of these little things out of it, we would call the thickness of it dx, a very, very thin change in the x direction. At least how we have this drawn, it'd be a very, very thin change in the x direction. And so the volume of this little very, 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 very thin cylinder, that's because that's what it is, right? It's a little very thin cylinder, a very thin disk. That is the area of the circle times this thickness dx. Would you guys agree with that? The volume of this little tiny slice that I'm making would be the area of the circle times the thickness. True? That's how you find the volume of any cylinder, right? The area of the circle times the thickness of the cylinder, or the height, we sometimes call it, right? Yes or no?
Yes.
Okay.
Yes.
Now, imagine that instead of just slicing out one little piece here, I sliced out, you know, maybe I sliced this thing into 10 little pieces. Okay? If I, and let's say that, you know, they're not this tiny, tiny little thinness anymore. They're just 10 slices of this. Well, how would I find the volume of the entire thing? I could take the volume of each of the 10 slices and sum them together, couldn't I?
Yeah.
Yeah, we should be able to. Well, what if instead of doing 10 slices of it, I did 100 slices of it, or 1,000,000 slices of it? All I'd have to do to find the volume of the whole thing would be to add together all 1,000,000 of them, or all, you know, however many of them I made. Well, what if I made an infinite number of these little slices? Well, all I would have to do would be to sum together all of the infinite number of slices of this cylinder that I've made, and that would give me the volume. And that's what we do when we integrate from A to B of the area of the circle, or the cross section, times the thickness of that cross section times the dx. Is we are slicing whatever shape we've got, and they're not going to be cylinders, because this is just a basic example to make life easy for the conceptual understanding here. But we're going to slice an infinite number of these little things off of here. We're going to find the volume of each one, the area of the cross section times its very thin thickness, and we're going to sum them all together from the first one to the last one. And that's what we're going to be doing to find this volume of these somewhat weird looking shapes that are going to be hard to conceptualize. That makes sense what we're trying to do?
Yes.
Cool. So let's extend this a little bit further. Here I now have a cone, right? And now it's a cone, right? If I were to slice my cone like this, what am I going to get? I'm going to get a
Parabola?
I should get a parabola, right? And do we know the area of a parabola? not very easily, right? Not without having to do some extra integration to find the area of the parabola itself. So slicing it that way wouldn't be any good. But what if I sliced it this way and opened it up? What would the cross section look like?
Circles.
They'd look like circles, right? And if I were to have a very, very thin circle that I sliced out of here, what would its thickness be this time?
Dx. Dy.
Well, this time it would be dy because we're now moving up and down in the y direction. Okay? But we're still going to get a cross-sectional circle like this. So here's where the problem sort of starts, is that in the cylinder, each of these circles was exactly the same area. True? So it's very easy. Find the area of the circle, multiply it by dx, integrate, get your area or get your volume, right? But here, each circle, no matter where I slice it, right, doesn't matter. All of those circles are going to have a different area to them, aren't they?
Yeah.
Yeah, or since they'll have the same thickness of infinitely thin thickness, but they'll have a different cross-sectional area, and therefore each of these little pieces that I sum together will be different. But the good news is, if I can find a generic formula for the area of any circle by placing this, let's say, in a coordinate plane, I should still be able to find the volume of that solid. Does that make sense to everyone? Hopefully that makes sense. All right, so now what we're going to do is we're going to make this even more complicated. So hold on one second. Okay, sorry about that. So we're going to make this a little bit more complicated now. So what we're going to do is, suppose we had some sort of weird looking shape here, like this. Okay. But I knew that when I sliced it, no matter how I sliced it, horizontally, let's say, that when I opened it up, these cross sections were still, let's just say they were circles. Okay. I should still be able to find the area of the cross section, and I should be able to use the thickness as a dy if I know this function's equation, or this, this one's not particularly a function, it's a function of y in terms of x, or sorry, function of x in terms of y. If I knew that function, I should be able to use it to write a generic formula to represent the area of any of these circles that I might get with cross sections that looked weird like this, and still be able to find its volume. Does that sort of make sense? It's kind of like using this. This one, I have a linear piece, right? But I'm still getting circles. Well, here I no longer have a linear piece, but if this thing is rounded, if it goes around perfectly round, so that each of these things creates a perfect circle, and we get some sort of smooth looking weird object there. It still has cross sections that are circles. I should still be able to find that volume by summing together the volumes of each of the little discs. Does that make sense?
Yeah.
Yeah. So that's what we're going to be trying to do, except we're not going to be doing it with just circles. Suppose we're going to be doing it with just whatever shape we want. So I might say something like, well, I've got a oh man, I can't draw. This is the part that I struggle with, is the drawing part. Hey, that was not half bad. There's a square pyramid. Yeah, that's really great. There's my square pyramid, right? Well, we know the formula to find the volume of the pyramid probably, but I do know that if I slice this thing perfectly vertically, that the thickness of each of these squares that I get as cross sections is dx, and that every cross section will be a square, and that I should be able to use the formula for the area of a square, right? The side squared times the thickness, dx, should be the volume of it, and I should integrate it from a to b to find the entire volume of it. I just need to be able to write s in terms of x, right? Up here, as I was trying to do it maybe with a cone, it would look something like pi r squared dy. And I would just have to be able to write the radius in terms of y. Does that make sense?
Yeah.
Right. So we might have squares, we might have rectangles with a height that's twice the length, or we might have an equilateral triangle for the cross section, or we might have semicircles or quarter circles as our cross sections. And we're going to get some really weird looking shapes. And that's the whole concept and idea of what we're about to try to do. I know that's a lot of setup for it and a lot of me just talking without any problems, but hopefully that makes sense.
Sort of, yeah.
Okay. Yeah, this is the one topic that I was most concerned about teaching online, that I think it's going to be the most difficult for people to comprehend, because it's usually the most difficult for people to comprehend anyway, because the shapes are so just weird. But let's give it a try. So the way everything that you will see that is a cross-sectional volume problem will be oriented. It will always be oriented so that the base of what you are looking at is some function in the xy plane, and that it will say that the cross sections will be coming out towards you. Basically, if you're sitting on the, looking at the table with a paper on the table, it's coming up out of the table at you. Or if you're looking at the screen in front of you, it's coming straight out of the screen right at you. So I'm going to do my best to sketch these as we go through them, but the pictures don't always look super great. So what we've got is we've got the base of a solid is the region between y equals 2 root sine x and the x-axis from 0 to pi. And if you don't know what that function looks like, that's totally fine. Oh man, it doesn't look like that. It looks about like that. It looks very similar to a sine function. It's just got a bunch of these with gaps in between them. But we only want the one from 0 to pi. So this is the base of the solid. And coming out of that, straight out of the screen towards you, is a bunch of squares. Okay? So if I were to slice this vertically and open it up, what I would see would be a cross section that's a square. Right? And so I'm going to just draw a bunch of little squares in here that are theoretically popping straight out of the screen towards you. And it's a little hard to conceptualize, but you've effectively got this front side of it that's that would be, if you've got the screen directly in front of you, if your screen is perpendicular to the table it's on, then this front side of this thing, this object would be parallel to the table that you're currently working on. I don't know what a crusty crab is, so I don't think I can answer that question. It doesn't look like a crab, nor does it look crusty. I don't know. And I don't know what you're talking about. Cool. I'll have to look that up. maybe, I don't know, that's making me nervous now. And it's going to curve out, and it's going to have a flat-ish top to it from these things here, but it's not going to be completely flat because some of these squares will be smaller. So it's going to sort of, it's going to rise up with like a sort of flattened side, but it's also going to then curve right back down. From SpongeBob. Oh, Lord. Children are weird. Okay. Let me look it up and see now if I can, let's see what my phone says. Krusty Krab. Sure, yeah. That is actually not that bad of an analogy for what this looks like, except that I don't know if any of you, I mean, if you've got your phone next to it, you don't know what a Krusty Krab is either, although you're all children, so you probably know. That's not a bad analogy for it. The base, and then you've got these semicircles, or in the case of the picture I'm looking at, it looks like you'd have semicircles sticking straight up out of it. Well, we've got squares sticking straight up out of it. But the base of the region of the thing that you're looking at there, it looks more like a rectangle. Our base is like this. So it doesn't quite look exactly like that, but it's that kind of concept. So what we want to do then is we want to find, first off, what is the thickness of one of these squares? Is it going in the X direction, or is it going in the Y direction for the thickness of it, right? Remember, these are tiny little slices that I'm cutting through here vertically.
The X direction?
It's in the X direction, exactly. Right, so the thickness is going to be dx. And what's the area of a square? In general, it's just the side squared, right? So what we want to do is we want to integrate from 0 to pi, one side squared dx. And so what we need is a generic formula for the length of a side of these squares, right? Because they're all differently sized squares, right? True? I mean, this little square is not the same size as this next one, which is not the same size as this one or this one, and so on. Agreed?
Agreed.
Okay. So what is the length of one of the sides? Let's just pick this biggest one that I've drawn. What is that length? What is S?
The Y value?
It's just the Y value, right? Well, what about here? It's just the Y value, right? No matter which square we choose, the length of that side is whatever the height of my function, right? S is equal to Y, which is equal to 2 root sine X. So we should be able to rewrite this as an integral from 0 to pi of the side squared, which would be 4 sine X, times the thickness of each of those. So the integral from 0 to pi of 4 sine X dx. Good or no?
Good.
Great. What's the integral of 4 sine X?
Four cosine. Sorry, four cosine.
Negative 4 cosine X. Somebody asked me to go back and repeat what I was just saying. So the side length is always from the x-axis to whatever the height of the function is. So if I've gone over x equals, let's say, pi over 6 units. Well, pi over 6 is sine is a half, and the square root of a half is 1 over root 2. So if I multiply that by 2, it's 2 over root 2. So the height of one of those is 2 over root 2 if I've gone over pi over 6 units. So 2 over root 2 squared would be the area. Okay, or just root 2 squared. Same thing here. If I've gone over pi over 4, well, the height is 2 times the square root of sine of pi over 4. If I've gone over pi over 2, then the length of the side of that rectangle is 2 times the square root of sine of pi over 2, because that's what gives me the height of the function. Does that make sense to everyone? Okay, cool. And so now we'll just evaluate negative 4 cosine x from 0 to pi. What's the cosine of pi?
-1.
1, right? Yep. Minus, and then cosine of 0 is just 1. So, oops, not minus -4. Yeah, minus -4. Sorry. We got negative 4 times -1 minus -4, which should be 8 units cubed. And for this very strange looking object, it has an exact volume of 8 cubic units. Good or no?
Good. Let's just do another one.
All right, let's do another one. So we're going to use the same function, but this time the cross sections are going to be equilateral triangles running from the x-axis to the curve. So these are coming straight out of the screen directly at you. Right, straight out of the screen directly at you. So this time this shape sort of got this ridge along to it. It starts here and goes up and then comes back down and hits this. It's a point right here again. And we've sort of got flattish sides to this thing. And we want to sum together all of the volumes of all of these tiny little triangular prisms that we can make out of this. So the first thing is we need to find the thickness. And what's the thickness of one of those?
Dx.
Should be dx again. And what's the area of an equilateral triangle?
Root 3 over 4 s squared.
Exactly. And if you don't know that formula for an equilateral triangle, if you just know the area of any triangle is 1/2 base times height, memorize this one for an equilateral triangle. The side squared times root 3 over 4. Very helpful. So what we need to do is we need to integrate from 0 to pi side squared root 3 over 4 dx. And all we have to do is turn s for our side into terms of x. And what is the side length? The side length is always
Value of the function.
the value of the function, right? S is equal to y, so squared, right? That should give us 4 sine x again. So we'll have 4 sine x root 3 over 4 dx, or just root 3 times, we can cancel out the 4's, right? That's the integral of sine, that's negative cosine from 0 to pi. So we've got root 3 times negative cosine pi, which would be 1. Right? Negative of -1 is 1, minus the -1 when you get cosine of 0 with a negative in front of it, or 2 root 3 units cubed. Good or no? Any questions or issues with that? All right, let's do another one. I'll give you guys a second to read through that one, and then we'll work through it. Everybody good? Ready? There's 2 sine x. We're just talking about one arch, which would be again from 0 to pi here. And this is the base of our region. And so coming straight out of this region directly towards you are a bunch of semicircles. And so this looks more like your little crusty whatever thing that you were trying to get me to look at. And so a bunch of semicircles popping straight out of here, except that each of them is a different diameter, different radius, all that fun stuff. Okay. So kind of got like a domed looking thing here with a little bit of an irregular side to it. Good or no? Okay. What is the thickness of one of those semicircles?
dx. I mean x. It's in the x.
It's in the x direction, so it's dx. And what's the area of a semicircle? Should be 1/2 pi times the radius squared, right? So all we need to do is integrate from 0 to pi, 1/2 pi, I can put that constant out in front, times the radius squared dx, which means what do I need to do with my radius? I need to put it in terms of what there? Right, in terms of x. Well, what's the radius of one of these semicircles?
Value of the function over 2.
Right, the radius should be y over 2, or just sine x. Good or no? So, radius squared, sine squared, pi over 2 times the integral from 0 to pi of sine squared x dx. Everybody good with that or no? Okay. How do we integrate sine squared x dx? Requires a trig identity, doesn't it? What's the trig identity that we need for that? I guess I'll have to tell you. 1/2 of 1 minus cosine 2x is the power reducing formula. You need to know the power reducing formula. It's on the sheet of formulas that I told you you need to know. or trig stuff. You need to know that. I could pull the 1/2 out. And the 1 should be easy to integrate. Should give us what? X. And with any luck, you should be able to integrate this negative cosine 2x, which requires a u substitution, hopefully just quickly in your head based on all the really simple little u subs that we've done. So what does that integral of negative cosine 2x become? It should be what? Negative what?
Sine 2x over 2.
Yeah, negative sine 2x over 2, or negative 1/2 sine 2x from 0 to pi, which gives us pi over 4 times pi minus 1/2 of the sine of 2 pi. Well, the sine of 2 pi is 0, so that's 0, minus 0, minus 1/2 of the sine of 0, which is also 0, which gives us pi squared over 4 units cubed. Good or no?
Do we put units cubed instead because it said that the linear unit is measured in inches, or do we just keep units?
I don't read problems. Inches cubed. Everybody good there now? All right, let's do one more of these. There's x squared plus y squared equals 1. Right? Isn't that what x squared plus y squared equals 1 looks like? Yes, it is. All right. Now we have cross sections that are perpendicular to the y-axis that are isosceles right triangles. So that means that I'm going to draw these like this, sticking straight up out of there, but now it's going to lay across this way. Does that make sense? What this looks like? A bunch of these little triangular cross sections sticking straight up out of the page at you. Good or no?
Yep.
All right, cool. So how are we going to go about this? What's the thickness going to be?
dy.
This time it should be dy, right? Because these are going in the y direction. And what's the area of one of these? It should be 1/2 of the side length, we'll call it the leg squared, right? Since it's 1/2 base times height, but they're isosceles right triangles.
Yep.
Yeah, everybody good there? Okay. Perfect, okay. Well, what is the side length? What does L equal?
How wide the function is?
So if we're going to measure this distance, we can't measure it all at once. We have to do each piece separately. How do we measure from the y-axis going to the right? As an x value, right? And if it's x over here, it should be identical another x over there, shouldn't it? Or no?
Yes.
Yeah. So what is the length of one of those sides then going to be? Should be 2x. Do y'all agree with that or no?
I agree.
Oh, good. All right, so if our length is 2x, then what does our area become? 1/2 of 2x squared, which should become what?
4x squared.
No, 4x squared divided by 2, so just 2x squared then in the end? Good or no?
Good.
So all we need to do is we need to integrate from y equals -1 to y equals 1, 2x squared dy. And so what's the problem that we have with that?
It's x, but we're integrating in terms of y.
Right, we got to integrate in terms of y from a y equals -1 to a y equals +1, but our function is in terms of x. So we should be able to just go right back to our original equation. And what does x squared equal? It should equal 1 minus y squared. So this can now become, I'll put the 2 out in the front, 2 times the integral from -1 to 1 of 1 minus y squared dy. Good or no? Hopefully so. 2 times y minus y cubed over 3 from -1 to 1 gives us 2 times 1 minus a third minus -1 plus a third. Or 2/3 plus 2/3, which is 4/3 times 2. Hopefully there weren't any units this time. 8/3 units cubed. Any questions on that?
It makes
Or any-
sense.
Or anything else we've done today?